Hi, and welcome everyone to this webinar about surface-to-surface radiative heat transfer. My name is Nicolas Huc. I'm working for COMSOL in France, and I'm responsible for the development of a heat transfer module. I'm especially glad to have the opportunity to present this webinar today, as surface-to-surface radiation is a topic that we have been working on quite a lot recently. So now we offer a set of capabilities and features that should be useful. So today I'd like to start by making a point about the case where surface-to-surface radiation is of interest in a simulation and when it can be skipped. After this first part, we will look at the details of surface-to-surface radiation, how to produce high-fidelity models for surface-to-surface radiation, so the wavelength and the temperature dependency of surface property, as well as the mixed diffuse specular surfaces and semi-transparent layers. Finally, we will make a point about how to carry on efficient computation. That will be time for Q&A. Hopefully, we'll have 15 minutes at the end of the presentation to answer your question. But feel free to ask questions during the presentation, and if I can, I try to answer the question as they come. Okay, so yeah, this part is really important, I believe, because sometimes the surface-to-surface radiation, the radiativity transfer, is not included in models, and it should. So it leads to inaccurate estimation of a temperature distribution. So really here the point is try to identify the condition that makes thermal radiation and surface-to-surface radiation important to predict the temperature distribution. I will not cover the radiation in participating media or absorbing media in this webinar, but we have enough content for today, but that's another field that is also covered by simulation with COMSOL Multiphysics. Okay, so to get surface-to-surface radiation with largest effect on the temperature distribution, first of all, we need a transparent media between two surfaces. That's quite obvious, but if we have opaque material everywhere, then there is no need to worry about surface-to-surface radiation, obviously. And then, which is also quite obvious, is that radiation is important when it's large compared to conduction and convection. And to get more in details for this point, this would be related to the surface property. So when the surface emissivity is large, so surface emissivity is something, it's a quantity between 0 and 1. So when it's close to 1, it indicates that the behavior of a surface is close to a black surface, so it's emitting the maximum that is possible. The surface-to-surface radiation will influence the temperature distribution when there are large temperature difference between two surfaces fronting each other. And also when we have an external source of radiation, the most classical one must be the solar radiation. When we have solar radiation, that's an experience that we had, all of us. Yeah, we can feel that the sun is heating surfaces, bodies, etc. So when we have external source of radiation, that was to be included in a thermal model. And of course, when conduction and convection are small, so there is one very obvious example is when you are looking into a space application with a vacuum between objects, then there is no conduction or convection. It's just the convection, the radiation that can exchange energy between two objects separated by vacuum. And there is one last point that I mentioned here is that related to the fact that the conduction is quite slow in material, convection is related to the speed of the fluid, and radiation is very fast actually. Radiation has the speed of a light, so it's almost instantaneous. And when you are looking at application for very small time scales, sometimes it's only the radiation that will influence the temperature distribution. So we can illustrate this concept through a couple of models that I've selected. So all these models are models that are available on our website. You can download them using the link that is given on the slides. So this one is the good old light bulb with a tungsten filament that is responsible for some light emission, but as you know, it's not very efficient and it's also dissipating a lot of heat. And in this case, we have good ingredients to make SAMA radiation large compared to the rest. In particular, the temperature of the filament is very high. It's more than 2,700 Kelvin. The surface emissivity of the tungsten filament also is optimized, so it's close to 1, and so it means that it will radiate a lot. So we have ingredients that make obvious that we should account for SAMA radiation if you want to predict correctly the temperature distribution in such a model. Another example, I mentioned the solar radiation. In this model, we try to explain and to predict the temperature distribution of these two boxes, this one and this one, during a day. So as the sun moves, or the shadow of the sun moves on the floor, one box receive the SAMA radiation during all the day, while the other one is shadowed during a period, and of course it has some impact on the temperature distribution of the box, and obviously this is something you cannot predict without accounting for SAMA radiation. Another interesting example, because this one I would say that it's not obvious at a glance that SAMA radiation play a large role. It's if you consider a room where the floor is at 15 Celsius and the ceiling is at 25 Celsius, so the cold on the bottom and the hot on the top. Due to that, you will not have any natural convection, so the air will be immobile, provided you don't have any fan or something like that. And then you can quite easily estimate, of course, the heat transfer by convection. It's zero because there is no motion. By conduction, you know that air is a very poor conductor, so it's less than 1 watt per square meter that is exchanged between the floor and the ceiling. And the radiation, if we assume that we have a surface emissivity close to 1, then we are close to 60 watt per square meter. So this is a case where we don't have any extreme temperature. We just have small convection and conduction. So for this reason, the radiation take over. And if you want to estimate the SAMA loss of energy efficiency of a building with room with this kind of configuration, you really need to account for SAMA radiation. Okay, and one example that is very interesting because you don't have a simple answer is electronic cooling. In electronic cooling application, there are some applications where you really have to account for SAMA radiation, and other one where you can skip this part of the model and still get accurate temperature distribution. And to answer more accurately to this question, you need to consider the type of cooling. For example, if you're interested in passive cooling, noiseless cooling, where you don't have any fan and you just rely on natural convection to get some cooling, then it's pretty small, and SAMA radiation is likely to be important, maybe not dominate, but at least to be important. And on cases where you have fans and active cooling, then the flow motion is probably big enough to dominate, and then SAMA radiation is very small compared to convection. And actually, we will exemplify this through a very simple example that I will open in COMSOL Multiphysics. So it's in this model, we have a chip here that dissipates 10 watts. And on top of this chip, we have a heat sink and a flow, but it's a moderate flow that is going through the fins. And the question is, if the surface emissivity of a heat sink is large, close to 1, do we need to account for SAMA radiation or not? So this case is a little bit on the edge, so there is no obvious solution, and maybe that's the safest option is to try it in a model and to compare both models, the one just with heat transfer and flow, and the one with heat transfer, flow, and thermal radiation. So let's jump into COMSOL Multiphysics. So here I have a model that is already built. You can see that we have a geometry, we have some materials that are defined here, aluminum, air, etc. We have one physics interface for heat transfer. So heat transfer in fluid and solid. So we have a solid part here, which is made of a chip and the heat sink. We have a fluid, of course, and we have some temperature inflow condition and outflow condition, for example. And on top of that, we have a flow that is defined. So with inlet and outlet. So we don't see the inlets, we just see the edges here because some parts of the geometry are hidden to make it easier to analyze. But here now I'm showing everything. So we have inlet and outlet, and everything is coupled through multiphysics coupling non-isothermal flow. So which means that we are solving both heat transfer and flow together, and we get the cooling due to conduction and convection in this model. The model has been solved already, and we have a temperature distribution and a velocity field. So we can see that the maximum temperature is about 90 Celsius. So now the question is, how can I update this model to account for thermal radiation? Actually, it's pretty fast. We go back to the model here, and there is one option to add physics. So we'll go for that. In the heat transfer directory here, we have a radiation folder, and we can pick surface-to-surface radiation like that. Just double click on it, and it's added to the model. And then I can define the boundary where I want to apply surface-to-surface radiation. So the boundaries where I want to apply is all the heatsink boundaries here, and also on the walls of the channel. So I can select them like that and say that I want to solve for surface-to-surface radiation on these boundaries. Then I have to specify the material property. So to make it simple, I will set the same property on all boundaries. So for the diffuse surface that is defined here, I will keep the option that says that the radiation is controlled by the opacity. So by default, the fluid domain made of air is transparent, and the aluminum is opaque. So the radiation will travel in the air domain. And the surface emissivity can be defined directly here. I can say that it's 0.9, for example. And because I mentioned that the radiation is opacity controlled, I should specify the opacity of the exterior of the domain, what is not part of the geometry. And this can be done through this opacity feature here. And there is one, which is a kind of COMSOL wording, the voids, the infinite voids, what is around this geometry. And I can specify that is opaque so that the radiation will not go outside, but just between the wall and the heatsink. So I have defined the surface-to-surface physics interface, and now I just have to link it to the heat transfer interface by a multiphysics coupling, which is available here, heat transfer with surface-to-surface radiation, to apply it on all boundaries. So the one where surface-to-surface radiation is not defined are automatically removed, and we see that here it's coupling heat transfer and surface-to-surface radiation, so there is nothing to change to the default settings. And just doing this is enough to include surface-to-surface radiation in a model. Then I can solve. That would take 1 or 2 minutes. I'd like to save this time for the rest of the presentation. So I'm going back to the presentation and showing directly the output of the simulation. So on the left, maybe you recognize the first temperature profile that I showed. And we recognize the 90 Celsius maximum temperature. And on the right, it's what we get if we solve the model that I just updated. So we see that there is actually a temperature difference between the two cases. A temperature drop by something like 11 Celsius or 11 Kelvin. Yeah, that's up to everyone to conclude if it's important or not. But for this application, it could be very well that the maximum operating temperature is 85 Celsius. So if you don't account for thermal radiation, you overpredict the maximum temperature, and and go above this temperature and all with thermal radiation and good emissivity of the different surfaces, then actually it's possible to dissipate some heat and to remain below 80 Celsius. Okay, so that's conclude my first part about when we can use and include surface-to-surface radiation in model and in order to get a better description or prediction of a temperature field. And now that hopefully we have some guidelines, let's look at the details of how to model thermal radiation. So slightly theoretical slide here, just to recall that what we call thermal radiation is electromagnetic waves, and these electromagnetic waves have different wavelengths. And if we consider a black surface, it will emit radiative intensity at different intensity and wavelengths depending on the surface temperature. So this is what is defined by this formula here, that gives radiative intensity as a function of the wavelength and the temperature from this this definition that we don't really need to comment here, but rather to look at what it looks like on this graph. So on this graph, we have the wavelengths on the x-axis, and on the y-axis as the radiative intensity, and we see different curves, different colors corresponding to different surface temperatures. So what is obvious is that for high temperature, we get high intensity, but we also see that the distribution, the spectral distribution shifts. So for high temperature, we get short wavelengths, and for lower temperature, we get larger wavelengths. So just this to say that depending on the surface temperature for black bodies, we get different spectral distribution. And then if we consider non-ideal black bodies, but gray bodies, for example, then they have a surface emittivity that can be wavelength dependent. So depending if radiation is coming from a hot source or a moderate source, it may behave differently depending on the surface property. So what I suggest now is to review a couple of models to represent this in a simulation. So the simplest model, and if you're lucky, that would be sufficient, is the gray, diffuse gray surface model. So for gray surface, we assume that the surface property are not wavelength dependent. So it's sometimes true or almost true. So here I plotted a curve that is almost constant, and so it's, for example, the emissivity as a function of a wavelength. So in this case, it looks safe to approximate the small variation by a constant value for all wavelengths. So in this case, you can use the gray surface model and assume that all the surface property are constant. This is also a model that you can use when you have a limited wavelength range. For example, if you have surfaces at 300 Kelvin and 700 Kelvin, you can say that most of the radiative intensity will be in this range here. So even if the surface emissivity is smaller for very large wavelengths or for very small wavelengths, since in your model there is no radiation with these wavelengths, then it's safe to approximate the surface properties as constant as well. The interest for using this model is that it's simple. You just need one value for all spectral bands, and also effective from a computational point of view. You get less degree of freedom to solve for compared to the other models. So the other model is when these hypotheses are not valid. One still simple and useful model is the surround ambient band model. So in this model, the starting point is the fact that if we look at the radiation emitted by the sun, which can be approximated more or less by the spectral distribution of a black body at 5,700 or 800 Kelvin, we get almost all the radiative intensity with a wavelength smaller than 2.5 micron. And if we look at the spectral distribution of radiation emitted by a black surface at 700 Kelvin or lower, then almost all the radiative intensity is emitted with a wavelength larger than 2.5 micron. So in other words, there are two separate range of spectral bands, one for the solar radiation and one for the infrared radiation that is emitted by the object at classical temperatures. So the idea here is to define one material property like the emissivity for the solar band and give another value for the ambient band. And just doing this, so of course it duplicates the degree of freedom you have to solve for radiation, so it's more expensive than a gray model, but it gives some details, additional details in the model description, and that's something I would like to illustrate with a very simple model. So the model is a block made of concrete. This block is receiving irradiation from the sun, and it's also emitting radiation to the surroundings. So it's heated and cooled by radiation. So for simplicity, I will skip in this particular model the convection due to the surrounding air, maybe the conduction due to the contact to the ground, etc. So just focus on radiation, and I will solve for stationary state, which does not exist obviously for the sun, since the sun is constantly moving. But just to make things fast and easy to solve, I will take this rather crude hypothesis, because the idea here is to compare the equilibrium temperature when you assume that you have a gray surface, so with all the surface emissivity equal to 0.6. Then the same thing when all the surface emissivity are equal to 0.9, and then we'll use the solar and ambient spectral band model and take values that are actually closer to the reality for concrete. So a surface emissivity of 0.6 for the solar band and 0.9 for the ambient band. So let's again open a model that I prepared to save some time. So the model contains just a block. The block is made of concrete. We are solving for conduction in the block, and we are solving for surface-to-surface radiation for the surrounding for the surfaces. We have a surface property here. So by default, we have a gray surface model. So you can see that the surface emissivity here is 0.9. And we have an external radiation source, and I selected a source defined by the solar position. We take the solar position in Boston today at 12, and yeah, we are quite optimistic on the radiated intensity. So we expect 1,000 watts per square meter. That is a very clear sky. I'm not sure that's reasonable for winter, but any value will lead to the same conclusion. Okay, so this is the first version of the model that we can solve already. So I recall that we are using a gray surface model with 0.9. We can compute the solution. Yeah, with this simple geometry, it will be very fast, and we are not solving for the flow. So we get temperature distribution, and yeah, we can see that it's about 95 Celsius or so. So now we can compare this result with the same simulation using 0.6 for the surface emissivity instead of 0.9. That should be very fast to get the solution as well. Okay, so we see that it's slightly lower. It's maybe 91 or 2, but still close. And now what I would like to show is how to switch to a solar and ambient spectral band model. So I'm going in the surface-to-surface radiation settings. And for the wavelength dependence of surface property, instead of constant, I choose solar and ambient. And if you do that, you can adjust the endpoints, the 2.5 micron that I mentioned before, but I'm fine with it. And if you go back to the diffuse surface property, then you see that it's possible to define, for example, the surface emissivity for each spectral band. So for the solar band, I will say that it's 0.6, and for the ambient, I will say that it's 0.9. Okay, and that's all I have to change in my model, and now I can compute and solve again. And we see that now we get a really different temperature distribution. It's only 75 Celsius now, and it's due to the material property, the surface emissivity, which is no longer homogeneous, and so that more radiation is reflected, so less is absorbed from the sun, and more is emitted on the ambient band. So we get a lower temperature, which is logical, but you can predict that only with different property for the solar and for the ambient band. So I see that I have received a number of questions. I try to check them and answer them directly if possible. We will answer all the questions after the webinar, but if I can answer already, I will try. Okay, so one question is obviously from a user from COMSOL that is not new. He has been using COMSOL Multiphysics in the past and asked what happened to the surface-to-surface property that was previously included in the heat transfer interface. We decided to split it to make things more modular, and also we are expanding the capabilities of surface-to-surface radiation quite a lot. So it was making too many option and choice in a single interface. So now we restructured it, and also we see this as a multiphysics coupling. That was already the case, but it was kind of hidden. So yeah, it's both for, I would say, consistency and usability that we decided to split. So if you have old models, they are still working the same, but if you create a new model in version 5.4, that's the way to proceed. There is one additional question. So if you just add surface-to-surface radiation interface, that's a question. Does it account for conduction? No, you need really to couple the heat transfer in solid that computes the temperature field, the T-dependent variable, with the surface-to-surface radiation, and couple them through the multiphysics coupling. That's the way to proceed. One other question is about the licensing. The surface-to-surface radiation interface is part of the heat transfer module, so you need to get the heat transfer module to access to it. And okay, one interesting question about radiative cooling. I will say a little bit more about this, so I keep it for later. There is also the question about the ambient temperature. So when there is no object facing a surface, what is the temperature of the surroundings? I understand the question like that, and the ambient temperature can be defined here. So in this model, the ambient temperature was 20 Celsius, but of course you can change for something else. I see that we are getting a lot of questions. Maybe I will go forward with a presentation to make sure to reach me, and I'll keep an eye on the question and keep answering them. Thanks very much for asking all these questions. Okay, so to answer some of them, I would like to present the alternative option when the gray surface of a solar and ambient surface model is not sufficient. Then actually you can define as many spectral bands as you want. So this is called in COMSOL Multiphysics the general diffuse spectral surface model. It's also known as the box model. So the idea here is that you define different spectral bands, again, as many as you want. And on each spectral band, you assume that you have constant material properties. So it's like a gray surface model for each spectral band with a limited number of spectral bands. So to illustrate how it works, I represented here the surface emissivity of snow. So as you can see, the surface emissivity of snow range between zero 0.1 and almost 1. So it could be surprising that snow has a surface emissivity of 1 like a black body, but this is for the infrared. And these two lines represent the visible spectral range. So on this range, you can see that the emissivity is low. So just like that explain why it looks like a white surface. But if you would see on a different range, the snow would appear as obviously not as white, but rather just like a black body. For the but just for the story. But now assume you want to include that in the model. Obviously, you need to do something to account for the change, and you can define, for example, 4 spectral bands. So 4 intervals, and in the user interface, you just have to specify the endpoint. So 0.3 micron, 1.2 micron, 2 micron. And then COMSOL Multiphysics will automatically compute the average property for each spectral band and approximate the surface property here, the surface emissivity by the red curve. So this works as soon as you enter the surface emissivity as a function of the wavelength. So epsilon here is a function that I prepared, and rad.lambda is a keyword for the wavelengths. Could be also a function of more like a function of wavelengths and temperature, but I just focus on the spectral band for now. And if you believe that this is not enough, you just have to add more endpoints here in the model, like this, for example. So you get more intervals, and then the sampling of a function is updated, and you get now the green curve. So what is nice is just have to adjust the number of endpoints, but you don't have to change the definition of original function. This is computed directly. Yeah, so about wavelengths dependent properties. So it's very interesting to define emissivity, reflectivity, transmittivity, or opacity as a function of the wavelengths. And the application are for if you have access to accurate surface property, then you can enter them in COMSOL Multiphysics. That's a good thing. Also, when you have one material, maybe that it's enough to take 1 or 2 spectral bands to represent it. But when you have multiple multiple material, they may have different spectral bands. So then you need to split your wavelength space in multiple bands, and that's quite easy to do. And there are some industry working, or some research working on particular coating or material with particular radiative property as a function of a wavelength, and someone asked a question about radiative cooling. So that's typically one application where usually you want a low emissivity for the solar radiation, and there is a gap for which the atmosphere is almost transparent. If I remember correctly, it's 8 to 13 micron, where you would like to have very high emissivity to emit as much power as possible. So to describe the surface property, that's straightforward with what we have shown here. There is a small manipulation to define I would say a kind of equivalent emissivity for the ambient, for the surroundings. So if you're interested in doing that, please contact me. I will guide you how to proceed. Okay, so to continue on the high fidelity models, now I would like to say a word, and I've seen that I had a question about specular reflection, diffuse reflection, and I will also cover semi-transparent layers. So what is that, and why is it of interest, again, to get high fidelity temperature distributions? So first of all, what happened to radiation when it reaches a surface? If you have a black body, then it's fully absorbed, and the black body in turn will emit some radiation depending on its surface temperature. If you have a diffuse mirror, the incident radiation will not be absorbed at all. It will be reflected in all directions. If you have a perfect mirror or a specular mirror, it will be reflected in a symmetric direction. And if you have a transparent layer, then it will be fully transmitted. So these are some extreme cases corresponding to different models for the radiation. And if you combine this model, then it makes it possible to describe quite accurately the real behavior of surfaces. So in reality, the emissivity, the diffuse reflectivity, the specular reflectivity, and transmittivity may not be 0 or 1, but something in between, and we just have to verify that they are positive and the sum is equal to 1, and then we get the representation, accurate representation of a surface behavior. And so again, is it important to predict the temperature distribution? And I prepared another example to illustrate that. So this example is a radiating surface. So you can think about a very hot surface radiating on the upward direction. On top of this surface, I placed a mirror, curved mirror. And this mirror will be either a diffuse specular or mixed diffuse specular, and that's what we want to study. But in all cases, the radiation will be reflected back. And finally, this radiation will reach a black surface, so will be absorbed by this black surface. And the question is, what is the heating, what is the temperature distribution of this black surface? Or to simplify the question, we will study what is the profile of a radiation, the radiation distribution when it's reaching the surface, depending on the mirror property. Okay, so I run this simulation with different value for the specular reflectivity, so from 0 to 1. And here I plotted the radiative intensity as a function of ρS 0.6 and 1, and we clearly see that there is a big difference between these radiation profiles. So this, maybe I can show the model to explain what it looks like. So I'm just focusing on the radiation, so you can see that there is no heat in this model. I added opaque surface for the mirror, and for the mirror I have surface emissivity and the surface reflectivity that are defined from a material. This material is available here, the mirror and the black surface, and we see that there is a parameter called ρS mirror that is changing for different computation, and this is controlled by our solver here. So we have this solver where we ask to range from 0 to 1 with a step of 0.2. So we are computing the radiation profile for all these values, and we get this this graph that I shown before. So the radiation distribution for different value of ρS, and we can see the difference. Or if you prefer, we can see the distribution, intensity distribution on a slice cut. So maybe I should show where it's plotted. So here we have this red line, and we are putting the radiative intensity on this red line as a function of ρS. And yeah, I can go back to the presentation where it may be more explicit. So we see that for a purely diffuse mirror, yeah, it's a very flat and diffuse profile, and for higher value of ρS, so the more specular it is, the more sharp the distribution is, and yeah, clearly we can predict that the heating will be very different between these cases. Okay, last thing I'd like to present for high fidelity model is the temperature dependency property. So I choose to present something that is quite extreme, but exists, for example, for silicon, where at hot temperature, the high temperature, the silicon can become semi-transparent. So here it's a simplified model where I assume that for low temperature, we have a purely specular mirror, and for high temperature, we get a fully transparent layer. So in terms of material properties, I would like to define in COMSOL multiphysics a transmissivity that is 0 till 500 Kelvin, and then rising, and at 800 Kelvin it's equal to 1, and then it's 1 for higher temperature. And of course, the specular reflectivity is related to it, since the sum has to be 1. So it's 1 for low temperature and 0 afterwards. So I will not start again going into COMSOL multiphysics. I prepared some screenshot. So to test how to model that, I created this 2D model where I have a core with an increasing temperature. So this part of the geometry will increase with the temperature will get higher and higher. So due to conduction, the rest of the model temperature will rise as well. And this semi-transparent layer here will get this property that I mentioned before. And we have two opaque surfaces, this one and this one. So when this semi-transparent layer is opaque, the radiation emitted by this surface is reflected back to the surface. And as soon as it becomes transparent, then the radiation is going through. And this is exactly what is shown here. We have, as a function of the time, the evolution of the average transmissivity of a semi-transparent layer here. So at the beginning, it's purely opaque, and the reflectivity is 1. And as the time increases, the temperature increases as well, and we see that the layer becomes transparent. And the dot line represents the total radiative intensity received by the external boundary, and we see that, of course, as soon as the layer becomes transparent, then from 0 we get to more than 2000 watts received by this external boundary. So how to do that in COMSOL multiphysics? You need to use the semi-transparent surface feature that is available in the surface-to-surface radiation. You need to define the material property. So from analytical function or interpolation function, you can define tau here for the fast transmissivity. The reflectivity is simply defined by 1 minus tau, and just solve the model, and you get what I'd shown before. Yes, that's the function that I represented. Okay, so before I take all the question, a word about computation, because I've shown a lot of things, you notice, but I haven't been able to run all the simulation live. It's because some of these computation are expensive, and so it's good to keep in mind that it's possible to save computational power by using some features. So first of all, if you don't need to compute the view factor, so it's just a convex object where all the surfaces are only facing the surroundings, then it's possible to just to use the surface to ambient feature, which is not in the surface-to-surface radiation, but in the heat transfer feature. So this surface to ambient feature is just defining radiative heat radiation between the surface and the ambient. It's part of COMSOL multiphysics, so you don't need the heat transfer model. It's very small. The cost to compute is very small compared to surface-to-surface radiation. So if it applies for your case, so again, if you have a single convex object with no shielding effect and not self-radiation, then you can go for that, and you will save a lot of computational power. And if you really have to use surface-to-surface radiation, which is the case most of the time, then you should think about the symmetry. If you are lucky, maybe that your geometry have one symmetry plane, so you can divide the geometry and the mesh size by two symmetry plane, or even 3 if you are lucky, so you divide by 8. And similarly, maybe you have some sector symmetry, and even better, you can have sector symmetry where every sector is symmetric itself. So in this case, you can divide the size of a geometry by the number of a sector times 2. So that's very interesting, and there is a symmetry feature in the surface-to-surface radiation interface. Why is it very interesting? It's because the cost of a view factor computation, so the cost in time and also in memory, is not linear. So it means that if you increase by 2 the size of the geometry, you increase by much more than 2 the assembly time and the memory use. So on this graph, I compare for the same model, the blue line represents the computation cost for the full geometry, and the red line represents the computational costs with 3 symmetry planes. So if you divide the number of degree of freedom by 8, here you get the assembly time as a function of the number of degree of freedom for surface-to-surface radiation. So you can see that you gain a lot. And that's the same here. The memory use is greatly reduced when you can take advantage of a symmetry. So for small number of degree of freedom, it doesn't care really, but when you get more than 100,000 of degree of freedom, then you really start to feel the difference. Okay, so now I've seen that I received a lot of questions. So I will go to the question just after this wrapping up. What I try to present today is first of all that surface-to-surface radiation is something of interest in heat transfer models and is often needed to predict accurately the temperature distribution. It's not very long to set up, to update a model, to account for it. It may be long to solve, but not to set up. So for you, it's not difficult. It's for your computer that it can be costly. And there are a number of options that we have introduced for high fidelity modeling for surface-to-surface radiation. So the wavelengths and temperature dependency, the different kind of reflection, diffuse and specular, and the transmissivity. So I hope that will be helpful. And now we have something like 15 minutes to go through the question. So yeah, I try to start from the point I left. So someone had a question about the external radiation source. So I guess that was for the concrete example. For the external radiation source, here you have multiple options. If we start at the beginning, you can specify a point coordinate, and this point will radiate either an intensity and a distribution computed from a blackbody model, or something user-defined per band. You can do the same for infinite distance. So the difference is that you get parallel radiation direction. If you take infinite distance, that's typically that would be useful for the sun. But for the sun, we have also a dedicated option. So where we compute the sun position as a function of a time and of a spatial coordinate. So the spatial coordinate can be defined from a predefined list of cities here, or from a coordinate directly, or you can also link this to the weather, to the climate database from ASHRAE, where there is thousands of weather stations, and they are coming with their location, so then you don't have to type the location yourself. Okay, so next question. Okay, someone is asking when you have an enclosure. So when I guess you are not facing any ambient domains, is it? The question was, is it possible to turn off, minimize the ambient radiation? I made this test a number of times, and what I can tell you is in a model like this, you can check how much of the ambient surrounding is seen by a surface. So if I change this plot here, I can ask to plot the ambient view factor for one spectral band or the other. And if you do that here, you see that it's exactly equal to 1. And if you have a closed enclosure, it will be 0. And if it's not 0, then you should double check the geometry and the mesh to make sure that there is nothing wrong. But if there is really something like a small error, you can always minimize the loss due to ambient surroundings by defining ambient temperature that is equal to the surface temperature. So this is here. Um, Yes, you can say that the ambient temperature is equal to the surface temperature, so you have no exchange in this case. But I would say this is a trick, and this is my experience is that it's not needed, but you know how to do. One question is it possible to specify angle dependency of emissivity for um, yeah, angle dependency of emissivity or reflectivity, I guess. This is not available, I would say, not yet. We actually we have a machinery that um, has been in a way prepared in this direction, but it's not fully ready, and actually we yeah it's more work. So if you have practical application where you would like to use that, if you have use cases, I would be very interested if you can describe them, and so that we can see uh, what we can do to address the application you are interested in. So please yeah, report any use case that you would like to be covered by event interface. One question, I guess, was about the maximum surface irradiation. Why it's not 1,000? I guess that was for the concrete example. It's just because the angle between the surface and the sun is not uh, yeah, the rays are not perpendicular to the surface, so you get less intensity. Okay, so yeah, something I didn't took time to explain, but it's important. The we have three algorithms to compute the view factors. One is the direct area integration. It's very fast, but it's limited to very simple configuration. So often it's too simple, but could be useful if you want fast computation on simple configuration. MECube is the default algorithm. So these algorithms suffer from the fact that it's not able to account for specular reflection or semi-transparent surfaces. So if you want to use specular reflection and semi-transparent surfaces, you have to use the ray shooting algorithm. As soon as you do that, then you get access to semi-transparent and opaque surface. So that answers some question I've seen. Yeah, more question. So one question is about solving a model, a time-dependent model. So obviously, that's possible. I should show open here the parasol model that I have already mentioned. So in the library, in thermal radiation, you will find a number of models, and this model is solving for surface-to-surface radiation, with radiation coming from the sun. And it's also solving for conduction. There is no convection, but you could also include convection. And for example, the external radiation source is updated. The position is updated from the time defined by the solver. So we have a time-dependent study, and in the time-dependent study, then we solve, for example, for the temperature in the two coolers as a function of the time. So you see that it's a time-dependent study, and you get a temperature distribution, which is a function of the time. You can browse the temperature distribution like that in this model. Okay, so one question was about the difference between made surface and Chinese surface. So I guess that will correspond to diffuse and specular are the surfaces. That's I guess what I shown in the example with a curved mirror. Um, okay, one question about related to the gap between two fins and the optimization. So I haven't covered at all the optimization capabilities. That's yeah, another topic. But if you're interested in optimization, there is an optimization module in COMSOL Multiphysics, and there are a number of algorithms that make it possible to do parametric optimization, shape optimization, or topology optimization. Topology optimization, I would not say that that's something really doable at this point for surface-to-surface radiation, but shape or parametric optimization are definitely options. And you can combine the optimization tool with the heat transfer or the surface-to-surface radiation physics interface. So yeah, I got another question about where can I find the semi-transparent surface. So again, if you want to have access to semi-transparent surface, you have to select the ray shooting, and as soon as you do that in the boundary feature list, you will see semi-transparent surface. Okay, and the few factors are they computed for each element of the finite element mesh? Yes, actually, all the mesh, the boundary mesh element of the selected boundary. That's the case indeed. Okay, and I see that yeah, the time is flying. Maybe I will continue to answer the other question after the webinar. So yeah, we will send an email for all the questions for sure. And back to the presentation, I would like to say a few words if you want to keep in touch with us. So first of all, if you have questions, you can fill a form on our website on the contact page. If you are not a user of COMSOL, or if you want to try something but you don't know with COMSOL Multiphysics, obviously you can request a demo. If you're already a user, or if you have a demo, you can access to the product on the download page that is mentioned here. And otherwise, there is a lot of material on our website, starting by the product information, the application library, all the models that I've shown today, but hundreds of additional models are available for download. So you can download a PDF describing the model and the MPH file, so you can open, modify the models yourself. We have video galleries with tutorials. We have a discussion forum that is also pretty active, and I could recognize some of the names of regular attendees to the forum. So thank you for participating. And I'm sure that if you are familiar with COMSOL, you know the COMSOL blog with almost one post every day, covering a lot of application. Some I would say rather broad topics, some very technical topics. And for example, about optimization, a couple of days ago, we got a very good blog explaining how to handle optimization with COMSOL Multiphysics. But you get also a lot of posts about heat transfer. We are actually preparing more posts about radiation. So yeah, I encourage you to keep an eye on the blog as well. Thanks very much for attending, and have a good day. Goodbye.